Welcome back to a new episode of Who Gives a Sheaf? Today, we are going to, well, first, I need to finish convincing you that sheafification actually is a functor. I don't believe I fully confirmed this in previous videos. And using all the tools we've learned about limits and adjunctions, I'm going to prove to you that, in fact, this functor is left adjoint to the forgetful functor. I also haven't verified that the forgetful functor is a functor, but that shouldn't be too difficult. I'm going to leave that to you. You can always complain in the comments, drive up engagement, if that's what makes you happy. And I may listen to your complaints and add a video with more details. So how can we do this? I mean, we could prove this big square diagram with the Homset version. But I've already in previous videos done some work towards the perspective where instead we provide the co-unit. I got to make notes to remember which way it goes. From pre-sheaves, the identity functor in the pre-sheaf category, to the composition of sheafification with forgetting, and the co-unit. So these are natural transformations which satisfy some particular universal property. So one way to establish this adjunction is to prove these universal properties. So that's exactly what we're going to do in today's video. But first, let's review some stuff about stalks. So previously, I told you if we have a morphism of sheaves, I told you a particular way in which we might define, using that map, define maps between the stalks on the sheaves. But now we're going to discuss this in a little bit more of a categorical way. In fact, I'm going to prove that this respects composition. You can do it just directly. It's on maybe an easier proof if you do it directly in terms of equivalence classes. But I'm going to show you a sort of categorical proof that puts the definition of a limit to work. So with that in mind, let's consider, so suppose we've got this commuting diagram, or sorry, this composition of morphisms of actually even just pre-sheaves, and an open subset U of V. Then I have my restriction map from FV to FU, and both of these map into the limit, right? The stalk at X, which is the limit, over all the open sets containing X. And I can also, I'll just stack the diagram like this. So I can also take now my morphism phi V to get a map into GV, and phi U to get a map into GU. And these also both map into the stalk of G at X, so I'll call this W prime, containing X. This is GW prime. And now because I have these maps out of the FV and the FU, by the universal property that defines the limit, I know that there has to exist a unique map making this whole blue diagram commute, and that's what I'm going to call phi sub X. So that's part one. That's how we define it. But if you give me one moment here to simply pretend to be a cowboy, lasso this whole diagram, yeehaw, and move it down. Now, what I'm going to do is play this exact same game again, but with my morphism psi sub V, FV, sorry, not F, that should be H. And here will be HU, and this will be psi sub U. And of course, these map into the stalk, I'll call this W double prime, the stalk of H at X, And now by the universal property, so starting down with G, by the universal property of the stalk of G, I know that there's a unique map making this diagram commute, and I'm going to call that psi x. So finally, what I'm going to do is now take the composition. So I'll let this map here, maybe to give myself some space. This is phi composed with psi composed with phi at V. Likewise, over here, this is psi composed with phi at U. And now using the universal property of the stalk of F, so starting with these maps down here, I know that there's a unique morphism going right to here, and that unique morphism, well, that is exactly psi composed with phi sub x, but it's the unique morphism making this this big diagram with the red arrows all commute. But notice, I mean, you have to stare at this. This is something you just got to sort of do on your own and stare at it for a second. Of course, I could write all the details, but I'm not going to. But the point is the composition of these two maps also makes the big diagram commute. And so since there's a unique map that does that, we're forced to conclude that psi sub x, psi of phi sub x is psi sub x composed with phi sub x. So that's our fancy categorical way of proving that these maps compose. Again, you can check this for yourself in terms of equivalence classes very explicitly. And I invite you to do that and yell at me in the comment section to drive up engagement if you get stuck and you want me to produce an explicit proof for you. Okay. So now that that's out of the way, we can return to the story of sheafification. And in particular, I need to explain to you why sheafification is a functor. So we've said what it does on objects, but now I need to prove that if I have some morphism, phi from F to H, that I can produce a morphism of Fu plus into, so called this phi plus U. Sorry, it should be a morphism from Fu plus into H plus, but of course that means providing a morphism compatible with restriction maps for every single open set. So that's what we're going to try and do now. So how could we define such a thing? Well, remember that Fu plus, this is defined to be all functions U into the product of stalks of F over U, such that, I'm not going to have room to write the whole condition here, for all y in U, there exists, let me write it below, there exists an open set V, which we can sandwich in between y and U, such that, and so there exists an open set and some section of F over that open set where for every term, for every point in that open set, the germ of t at z agrees with the value of the function s, right? So that's what we're starting with. And we need to define some function. So I need to define psi plus u, apply it to s. So that's going to be some function, but now instead it will go into the product of stalks at h. That satisfies an analogous condition to all of this, but instead here we would have h of v. So what could we possibly try? So of course, in order to define a function, it's enough to define what that function does at every single point. And somehow it has to be built out of S. Well, S will take this point X, it will land you into stalks of F, right? So if I took S, I applied X, I would now get a stalk at X. And of course, there's a reason why I reviewed this induced map on stalks, what I could then do is compose this, so rather even just apply the induced map on the stalk at x to s of x. And now this is going to land in the stalk of g at x. So in other words, I have the correct kind of function. But in order to verify that this really does land in the image in h plus u, I need to verify this defining condition here, right? So let y be some element of u. Well, by the definition of f plus u, we can choose an open set v, which is sandwiched in between y and u, and some sort of section of f over v, such that for all points z in v, the germ of t is equal to the value of the function at z, right? So now I need to somehow come up with a corresponding, so using this, I need to come up with a corresponding section of g over t. But I have this map, phi v, right? That takes me from f at v to g at v. So if I apply phi v to t, this gives me a section of, h. I keep saying g. I don't know why I picked g, but I meant h. The sections of h over v. And so now I just need, so this is my guess at what's going to be the appropriate section to take, and I just need to check that it satisfies this analogous property, namely that the germ at every point agrees with the value of this function. So let's go ahead and compute. So given z in v, let's compute the germ of this section. So this is phi v t, computing the germ. Well, by all of our compatibilities of sheaf maps and sheaf morphisms, this would be the exact same thing as if I were taking phi, the induced map on the stalks at x from phi, and applying that to the germ, I should write z, apologies, and applying that to the germ of t at z, right? But then, the germ of t at z, this is just some point of v. T was the thing that we constructed that agrees with s everywhere. So this is the same thing as phi sub z composed with s of z. But wouldn't you know it, lo and behold, that's exactly our function phi plus u of s evaluated at the point z. And that's exactly what we needed to finish saying to confirm that this really does lie in the image of h plus u. Okay, so we're pretty close to, so now we at least have a map on the level of all the open sets. Is it going to be compatible with the restriction maps? Well, yes, of course, because it is just restriction of functions, right? Okay, I'll leave that to you to think about for a moment on your own. Yell at me in the comment sections if you like. I love extra engagement. And I'm also literally happy to make clarifying videos for you if you need them. So we have a sheaf morphism. And remember, what are we working towards? Our goal right now is to try and prove that sheafification is a functor. So we've described what it does in objects. We've described what it does in morphisms. We need to know that it respects composition of morphisms and that it preserves the identity. So let's suppose now, gosh, I chose a weird labeling here, but okay, let's say we have phi goes from f to g now, and psi goes from g to h. And so let's take so what is the sheafification of psi composed with phi, at u of some s in f plus u and evaluated at some arbitrary point of that open set. Well, by definition, we said that this is going to be psi phi at x applied to s at x. But at the beginning of this video, I gave you an abstract nonsense proof that this is going to be psi x of phi x of s x. And this is exactly, let me maybe move this over here. This is exactly psi plus u composed with phi plus u of s evaluated at the point x. So it respects composition. And lastly, but certainly not leastly, suppose we had the identity map. I'll just write it as I. The identity morphism from f to f. What is that going to do on f plus? Well, let's see. I plus u of s evaluated at x is going to be I sub x of s x. But now let's think about, here we'll do an explicit computation. What is ix going to do to some arbitrary germ? So let's say we have a vt here. What's it going to do to some arbitrary germ? Well, this is the map that it'll send it to v composed with ivt. But of course, iv is the identity, so this is just vt. And so sure enough, I sub x acts as the identity, so this is sx. And then therefore, indeed, I plus is in fact the identity morphism. So that finally concludes the verification that sheafification is a functor. Great. But now we still want to do the work to claim that this is the left adjoint in a pair of adjoint functors. And what we're going to want to do for that is, well, we can use our unit and counit. And this is because I actually started to define this in a previous video. So remember, we talked about that there's this universal property of sheafification that says if you start with any pre-sheaf f and a morphism and any sheaf g, and you look at the you forget g to a pre-sheaf, and then you consider the sheafification of f, forget back down to a pre-sheaf. Then I defined a sheaf morphism for you, theta, and I proved that there's a unique map f bar which makes this diagram commute. So this is exactly this is exactly the same universal property that one would use for the unit of adjunction. So to really just finish claiming that this is a unit, all I need to do is convince you that theta determines a natural transformation between the identity on the category of pre-sheaves and the composition of the forgetful functor with sheafification. Okay. So what do we need to do that? Well, we just have this commuting rectangle that we basically need to establish. That is, what I need to convince you of is that for any morphism, I don't know why I keep using h here, but I do. That's what's in my notes. I'm going to stick with my notes. Now, there's a bit of a conflict of terminology here. Oftentimes, for a natural transformation, we put the object in the subscript, but we're also putting open sets in the subscript. So I'm going to put the objects in the superscript so that I can put the objects in the open sets in the subscript still. So this will be theta superscript f, theta superscript h, and down below we'll have the forgetting of f plus and we will have the forgetting of G plus, and then down here will be the forgetting of F plus. But remember, the forgetful functor on morphisms, just because a morphism of sheaves is already a morphism of pre-sheaves, it's the identity, right? So this will be F plus. And I need to convince you this diagram commutes, which again means proving that for every open set, I just add the open sets in the appropriate spaces, that this diagram commutes, right? So let's go ahead and prove that. And well, first I better just remind you that the definition of theta sub u, that blue is a little too dark. That blue is a little too dark. The definition of theta u at some section S. So right, S is a section here. I need to define some function. We defined it in the sheafification video to be the function where for any input x, it just returns the germ of S at x. So let's go ahead and verify that this diagram commutes. So first I'm going to go around, I guess I'll go around this way first. So what is that? So I have theta u h composed with fu applied to the section S. So by definition, this is the germ of fus. Let me just see. Sorry, this is a function. So I'm going to plug in my test point x. By definition, this is going to be the germ of fus at x. But that, again, using all of our compatibilities, this is the same thing as f sub x applied to the germ of S at x. And what is that? Well, the germ of S sub x, that is the same thing as theta f u of S applied to the point x. And so lastly, but not leastly, this is exactly fu plus composed with theta fu s evaluated at the point x. So we have checked that both ways of going around the rectangle, or the square, I should say, both ways, these functions agree at every single point, and so therefore the diagram does in fact commute. So this concludes the verification that theta defines a natural transformation, and since we have already the universal property, we can conclude that this is a unit of adjunction. Incredible. But we do not want to forget about the co-unit of our adjunction. So the co-unit, I need to provide for you a functor, which is the composition of forgetting and then sheafifying into the identity on the category of sheaves on X. And we must also verify that it satisfies the universal property that for any pre-sheaf F and for any morphism from the sheafification into G, a sheaf, so down here I'm going to put I'm gonna drop writing forget everywhere because it almost does nothing, although you kind of want to be careful about what category you're actually in. It'll be a map, so eta goes from the sheafification of G to G, shout out sheafification of G, and in such a way that there should exist a unique map F bar that makes this diagram commute. Okay, so before diving into this proof, let me remind you that two sections are entirely determined by what happens at the germs. So what I mean by that is if we have two sections of G over some open set U, these are equal if and only if for all x in U, the germs of both of these sections are equal. One direction's obvious, right? If S is equal to T, then the germs have to be equal everywhere. And we proved this in a previous video, right? The converse direction says, well, basically, if these germs are equal everywhere, then that means that there's, for each x, we can find an open set Vx, where the restriction of S and T to Vx agree. But the Vx form a cover of U, and because we're assuming that G is a sheaf, we know that those glue together, that if they agree on all the restrictions, they must agree as global, as sections over U. So that's a trick that we're going to make use of here. Also, so we need to define what theta U is going to do, a map from G plus to GU. But actually, we already defined this map as well. So back in the Sheafification video, we proved that, well, one, there's a couple videos where I talk about Sheafification, but we proved that if you started with something that a pre-sheaf that already was a sheaf, and then you applied Sheafification, that it should be isomorphic. You should up to isomorphism get back the original sheaf. And so we're actually just going to use the map that we used in constructing that inverse isomorphism. So the map eta U. So we actually proved in that video that there exists, if G was already a sheaf, that we proved that there would exist some section of GU, which of course it depends on S, so we called it T superscript S. And it was essentially defined by the property that for every point in U, the germ of TS at X agreed with the value of function Sx. So we're going to take that property as given. And in fact, this does define a morphism of sheaves. So we still want to check that this defines a natural transformation, however, from this composite to the identity functor. So we need to write down another square and check that that diagram commutes. What is that square going to look like? Well, again, I'm just going to go ahead and plug it in at all of the at open sets. So let's see, we've got GH, we've got G plus. Again, I'm just being neglectful of writing forget. And again, I'm going to use this superscript convention just to keep track of which version of eta we're using where. And what do I need down here? I need F plus U. So we're going to verify that this diagram commutes. But instead of literally looking at this on the nose, on the level of elements, we're going to use this trick about the stalks. The two sections agree if and only if their germs at every point agree. So in order to prove that this diagram commutes, what we're really going to do is look at the composition both ways and simply evaluate at the germs and see that the germs agree everywhere, from which we can conclude that the sections themselves must agree, and so therefore the diagram really does commute. Okay, so that's our proof. That's our proof strategy. So let's go around. Which way do I want to go around first? I think I want to go around this way. Let's go around this way. So we're going to take FU composed with eta G U, and we're going to apply that to the function S. And we're going to evaluate that at some, evaluate its germ at some arbitrary x. Okay. But by definition, this is FU of, we already know, so the definition of eta G at U is the construction of some section T of GU depending on S. Right? So it's just FU of this, and we're evaluating the germ at X. But again, using all of our compatibility nonsense, this is F sub X at TSX. But TSX, Well, this map is also the same as applying the map f plus u to the section TS, and evaluating this. Right, this was a function where we defined what does that function do at x. It takes that section you started with and returns its germ at x, right? So this was the definition of applying f plus u to TS. But then in turn, f plus u got to pause for half a second to collect my thoughts here. Oh, I've made, it's a good thing I have my notes with me. I've made a mistake. I've made a mistake somewhere. So we want to go back here for a moment. I spent too much time on this video already to make any edits. So this is going to be fx. So remember, the defining feature of TS was that its germ everywhere should agree with Sx, right? So this was an important substitution that we need to make. So now, I apologize, sorry. This is what fu plus s at x. This was the definition of fu plus at x is supposed to be. But then now fu plus applied to s, that lives down here in h plus u. And remember, we're assuming that hu is a sheaf as well. And so we also know, by the same eta construction that we did previously, we also know that there's some section t of hu determined by the function fu plus s, whose section, whose germ agrees with the value at x agrees with the value of this function. So these things are equal. But I pretty much essentially just said in so many words that this is exactly what happens when we take eta h at u and compose it with fu plus s and evaluate that, take its germ at x. So remember, this is the germ of the result of going one way around the diagram, and we got there from considering the germ of the result of going the other way around the diagram, and therefore we can conclude that this diagram commutes. So we know now that our theta, as defined, is in fact a natural transformation between these pairs of functors. And actually, the universal property is now going to be very easy for us. How do we construct, in this case, f bar? Well, so we're supposing that we have some f given, and we already know from the sheafification video that our eta u is in fact an isomorphism of sheaves. So it has an inverse. And so the map that we're going to take from f plus to g plus is simply going to be eta inverse composed with f. So that's what we'll define f bar to be. And so by construction, it makes this diagram commute. And in fact, we need to show uniqueness. So suppose that G was some other sheaf morphism making the diagram commute. So that is, eta composed with G was equal to F. Well, again, eta is an isomorphism, and so multiplying by eta inverse on both sides, we can conclude that G is eta inverse composed with F. But that was f bar by definition, and therefore we have the uniqueness property, which completes the universal property defining the counit of adjunction. So that's basically that. We now have, well, we have now constructed the counit of the adjunction, and we have the unit of the adjunction, and so therefore we may at last conclude that we have that the sheafification functor is the left adjoint to the forgetful functor. Okay, so this is going to be a useful tool moving forward, and in the next video, we'll put it to work in some other fun and interesting ways. But now that you have a whole bunch of sheafy things in your toolkit, it's time to go prove some theorems about sheaves.